Hello everyone. Today I'll be discussing my research on the comparison of 1,10-phenanthroline, 5,6-dione, and 1,10-phenanthroline as ligands for heterogeneous single-site catalysts. My motivation for this project lies in its macro-scale industrial applications. Ethylene, which is a major component in the production of polyethylene, often has trace amounts of acetylene in its feedstocks. These trace amounts of acetylene can poison the polymerization catalyst for the production of polyethylene. Thus, to avoid this, typically palladium catalysts are used to hydrogenate acetylene to ethylene. The major issue with using palladium is its tendency to overhydrogenate acetylene to ethane. So, my research is to create ligands that can tune the properties of palladium such that it can preferentially convert acetylene to ethylene in an ethylene environment without overhydrogenating any of the ethylene into ethane. What I've been doing to tune palladium is manipulating the properties of the ligand such that they can't manipulate the properties of palladium. What I've done so far is compare the palladium loading of ligands with a dione backbone as well as substitutions at the 2 and 9 positions using dicarboxylic acid groups. What I want to do is use the ability of ligands to manipulate the oxidation state of metals to tune the selectivity of palladium and its reactivity. And I also want to see the effects of adding this additional possible binding site in the diketone on the selectivity and reactivity of palladium, as well as the effects of the carboxylic acid groups on the activity of palladium. What I like to note is that for a lot of these reaction syntheses, I've used the same reaction conditions. However, for some of the ligands, it's important to note the reaction temperature and pH and its effect on the production of the ligand, namely monocarboxy PDO as pictured here. This particular ligand did not follow the same reaction conditions as all of the other ligands, and you need to consider the pH as well as the reflux temperature in order to oxidize this ligand into monocarboxy PDO. You can see here in my ligand characterization the presence of some of the ligands that I've made. Here we have PDO. You can see the 3 proton peaks in PDO. It has symmetry, so even though there's 6 protons, there are 6 of the 2, each of them are the same for 2 of them are the same for each of the 6. Therefore, there are only 3 proton signals. Here you have the NMR spectra of dicarboxy PDO. There are 3 signals because also this ligand has symmetry. So the 6 proton signals that are replicated on both sides of the ligand are seen in these 3 signals here. Then in the monocarboxy PDO ligand, there's asymmetry, and this asymmetry is seen in the multiple peaks between the 7 to 9 ppm range, where most of my ligands have been, the protons for most of my ligands have shown up. But because it's asymmetric, there aren't 3 peaks as there are in the other ones. So you see the asymmetry, you see the multiple peaks that indicate the presence of the monocarboxy PDO ligand. Additionally, in this project, I focused on the method of catalyst synthesis. So typically what I do is dissipate cerium oxide into water and then add the metal and the ligand to create these single atom catalysts. What I've been doing this in a 1-pot impregnation. And also what I've been trying to do is manipulate the reactant order in order to see its effect on the palladium, the type of palladium in the system. So I propose different mechanisms that can alter the types of palladium seen, whether it's single atom palladium, metal clusters, or metal ligand complexes, depending on which reactants are added and in which order. Here I've highlighted the actual hydrogenation catalysis data. I like to note that dicarboxy PDO roughly consumes about 2 times as much acetylene at 120 degrees Celsius in comparison to PDO at the same temperature. Also, the amount of ethylene produced increases by about 1.5 times, and the amount of ethane produced decreased by 18 times with dicarboxy PDO over just plain PDO at 120 degrees Celsius. I also note the palladium weight percent for each of the ligands, and you can see here a trend between the between the dicarboxy-PDO and dicarboxy-phenanthylene, in which they have really high palladium weight percent loading because of the addition of the carboxylic acid groups. However, the same trend is not seen with monocarboxy-PDO and monocarboxy-phenanthylene because the monocarboxy-PDO used here was impure. But with dicarboxy-PDO and dicarboxy-phenanthylene, you can see the higher palladium weight percent loading, and in the dicarboxy-PDO, because of the presence of that diketone backbone offering another binding site, there's a much higher palladium loading. Here I show the XVS data of the palladium 3D orbitals. Here I like to highlight the type of palladium present in each of the ligands. For the most part, most of the ligands have palladium 2+, which is indicative of single atom palladium forming. However, for some of them, like the dicarboxy-phenanthylene and dicarboxy-PDO and a little bit of PDO, you see a bit of a shoulder at the 335 electron volt binding energy. So that's indicative of palladium 0 forming and that I have some palladium nanoparticles present in the system. Over here, I'm analyzing the reactant orders, and as you can see, for the very first one, there's a really strong palladium signal, which is for the addition of cerium oxide in water and then followed by the ligand and the metal. For the other reactions where I manipulated the order of reactants, the signal was not as strong, so that shows that the reactant order has an impact on the palladium signal seen in XVS. Lastly, I'd like to thank the Tate Lab and Dr. Yaroslav Losovich, as well as Indiana University and the Department of Energy for helping me with my research. Thank you.